Good afternoon, morning, or whenever to whomever. This is our, Brian, Vincent, Christian, and my heat transfer project video. For this project, we decided to analyze the increase of temperature over time under maximum load of the Samsung Galaxy S22, my phone. Originally, I, wanted to analyze the aluminum intake on my car, but we decided that trying to model the long block and finding the heat generated from combustion would be too challenging. After we decided against that, we decided to take a look at how the S22's surface temperature increases over time and compare it to the graph from ASTM C1055 on the correlation of time, temperature, and skin damage. To accomplish this, I downloaded a benchmarking app onto my phone and ran the test on minimum screen brightness and maximum SOC settings for 20 minutes in as much of an isolated room as we could manage. We used the FLIR camera provided to us from class to record the surface temperature over time. We pointed the camera at the back of my phone, and since the back is a matte black, the FLIR had no problem reading the surface temperature.
Here is our MATLAB SimScape simulation model for our Galaxy S22 SoC Snapdragon 8 Gen 1 heating up over time. So this takes place over 1200 seconds or 20 minutes, and you can see that we have a variable wattage starting from 13.5 going all the way down to 6. And this is on the actual CPU itself, so the Snapdragon. We're measuring the final and temperature over time of the CPU itself, of the back panel, and of the front panel. We're also measuring the convection heat and radiation heat in terms of watts for the back and front panels as well. In terms of conduction, we have about 8 different thermal masses here, and each of them cause for over a dozen forms of heat transfer. So each of these have to be taken into account because the phone is so small and so flat, and there's so many things inside of it that are also very small and very flat, that we have to sort of take all those into account because they have very large surface areas but not a lot of thickness. So they're able to fit a lot of them in there, and they each create at least some conduction. So we have to account for all of that before we can get a true accurate reading for our final temperature. So let's run the simulation and see what we get. So at the end of the simulation, you can see that our CPU, as expected, is the highest temperature, being about 51 degrees Celsius, with our back temp at 49 and our front temp at 44. So if we want to take a look at what our CPU looks at over time, you can see it starts at roughly room temperature here, about 22, and then it tapers off once it gets to about 51 degrees Celsius. So that's what you can expect your Galaxy S22's CPU chip to get to after about 20 minutes of hard use. This is during a benchmark, so it's experiencing some pretty heavy load. And it gets to just above skin burning temperatures if sustained for too long, so be careful. Now, of course, that's just the CPU chip, so the part that you're actually going to be holding is the front and the back, mostly the back. So the back panel, you can see, gets to about 50, just under 50 degrees Celsius after 20 minutes, which is still a little higher than it should be, but a little bit less scarring than the CPU is going to be. So now, the front temperature over time is the lowest. That doesn't even get to 45 degrees Celsius, but still pretty hot if you're holding it for a long time. So that's after 20 minutes, and that's when it starts to really taper off, as you can see. So if you want to take a look at the actual wattage behavior of the Snapdragon chip itself during the simulation, this is what it looked like, starting off at about 13.5 and tapering down to 6 over the course of that 20 minutes. And after about just under 10 minutes, it sort of levels out completely. So that's our SimScape model for our Galaxy S22.
Here's our SolidWorks model of the Galaxy S22. As you can see by the model tree, it's quite packed with features. We tried our best to mimic the most amount of materials and features inside the phone as possible, such as, the metal sides, the front and back glass, the PCB inside the SoC. Then, of course, you have, the heat sinks and stuff like that, and the batteries, We also have camera lenses in there, camera housing, and then we have EMF shielding to also provide some benefit in realistic scenarios for all the materials. Looking over to the SolidWorks FlowSim model tree, you can see that we have glass for the front and back glass, as well as the camera lenses. We have typical TSSOP, which is for the PCBs. We have aluminum for the heatsink and the IHS for actually cooling the processor and phone. We have steel for the bottom speaker housing, as well as the speaker unit itself. We have silicon for the SoC itself, which tends to be made out of silicon. We have PBT for the battery, which is the closest enough in thermal conductivity that we could find to lithium ion. Lithium ion was not actually an option when, going through these. And then for our EMF shielding, we went with the wood wool and slab, which seems to give us the best thermal conductivity that we could find as compared to what it actually is. Now, most of this model, you can see that I used iFixit, the S22 teardown video, to get most of these dimensions. Not a lot of this was actually measured. The outside of the phone was, because we have Evan's phone to measure, but the rest of it, we don't have that much. So the model is iffy on the inside. We did our best, but short of tearing it down and, getting every SMD and every little component in the phone modeled, there's no good way to actually determine how this model is perfect. We also don't know whether it's raw aluminum or whether it's some alloy of aluminum. We don't know if it's some alloy of steel. We don't know many of those things. So taking our best guesses at the materials and at the actual dimensions of these things is generally the best option. Now, if we're actually running the FlowSim, we were running at a mesh setting of 4, which based on the mesh, it's about 3 or 4 cells for the entire thickness of the phone, which isn't a lot in the grand scheme of things. We have a lot of things that are like 10 thousandths thick, 20 thousandths thick. So 4 blocks over the thickness of this entire phone does not give us an accurate representation. And so we determined that you actually need a mesh setting of over 7 to properly simulate all of this stuff. And a mesh setting of 7 would have taken days and days to run. So it is not optimal for us to test in that region. So that's another way that this model is not entirely accurate to real life.
To sum up the findings that we have for this project, you can see here that we plotted our real temperatures that we recorded with the FLIR camera in blue. We have our SimScape model in red, and then our SolidWorks model in green. So both of our models follow the same curve as the real temperatures that we recorded, and they roughly plateau at the same point, which is about 800 seconds into our working time with the phone under load. And one thing to note is that the temperatures actually do get to about 52 degrees. You can see in one of our captures from the FLIR camera that the back of the phone is actually at 51 degrees Celsius, which would cause some degree of burn to the hand if you were to touch it. And our team is somewhat confident that with both of our models following the same curve as the real temperatures, that we would be able to estimate and get in the ballpark of what the temperature of the SoC is during any point in our time study, which would range from 0 to 1200 seconds.